Alright, hello ladies and gentlemen, this is the first AP review video that I'm making, and let me warn you, this is going to be really rough. I'm still kind of getting myself familiar with the content on a weekly basis. Haven't reviewed at this level in years, so trust me, when you compare my Regents level videos to these AP level videos, there's going to be a difference. It might feel rough. I know it's going to be rough, but please bear with me. I will try my best to accommodate for all of you here and make things simple. Alright, so this here is about electric potential, and the first couple of topics we're going to cover in this video will be in the next slide. So it might not seem much, but there's actually a couple of stuff that we definitely need to go over in each of these four subtopics. Electric potential energy, electric potential for a point charge, potential for a uniform field, because there's a distinct difference there if you haven't paid attention in this class, and definitely equipotential lines. Some of these things, a few of these things, might have been repeated from our Regents level course a year ago for you guys. I might have done a little bit of review on that, so if you want to go back to Regents level basics, you might want to check out those old videos, but now we're going to bring it up to this high level for AP. And we're going to start with electric potential energy. Alright, electric potential energy, again, is a type of stored energy, stored based on position of these charges within the system and where they are relative to each other. And you could also equate it to work. It's the work done on a system of charges. So you'll see problems talking about work done on charges, potential energy changes. It's all pretty much calculated in the same manner. It's all joules, it's all energy. And we're going to calculate this with U equals K Q1 Q2 over R. Alright, now if you look at this equation, it's very familiar to electrostatic force. Energy here is not related to inverse square of distance. Here it's just over R, not R squared. And you need two charges to have potential energy to exist between them. So it's based on position towards each other, towards infinity, etc. Okay. And we denote it with the variable U. So maybe UE specifically, because U is typically potential energy. We need to denote it with subscript E to specify electric potential energy. Okay. So this is a scalar quantity. There's no direction. So energy is just energy. You just either you have it or you don't. But here, when you're calculating it, you need to have signs. So there is such a thing as positive energy and negative energy, to help us understand, especially with increasing and decreasing energy of a system. Alright, so if we look at this drawn example of two charges, positive big Q and positive little q, separated at a distance r, we could just simply calculate the potential energy between these two within each of them relative to their position to each other as kq times little q over r. And plus, we have to denote that both of them are positive, so we could still keep it as positive. And here we are going to have a positive potential energy. So right now it's sort of stationary. So we're thinking of this in terms of the energy they have stored up to do something, to do some sort of work based on their position. Because once we let them go, stuff is going to happen. They're going to move, they're going to push and pull on each other based on their signs of the charges. So we could think of this as the potential energy stored up to do something, to do some sort of work after you let them go. Because eventually, once you let them go, they're going to move, and that's kinetic energy. So we're going to see that this potential energy is going to start shifting over to kinetic energy once you let them go. Now, if we think of this sort of similar to gravity, we have potential energy relative to the Earth's core. When we change our elevation, change our distance away from the Earth's core, we also change our potential energy. We either gain or lose. The same thing is applied to these electric charges. And the way we have to think about it, we have to think back to work. So now let's say we want to move this little test charge a certain distance away from the source charge to the right towards point A, which is double the distance of where it was originally. So now we're going to sort of see, how does this change the potential energy of the system? How does this change the potential energy of this little charge here? So our original potential energy that I calculated at first, I wrote the expression up there. It's just U, positive U. Let's just call it 0 to denote this is like our original starting position. And then we're going to look at this, UA, as our new position. Still the same two charges we're talking about, but now here we see that with double the distance, it's sort of half the original here. Okay, so it's still a positive charge, but it's half of our original. So we're moving from a position of greater potential energy. Oops. Undo. No, don't do that. Oh, okay, it's all good. Alright, U is greater than that, so we lost energy. So therefore, this is loss of U, therefore, and so it's like a negative change. Okay. So we lost energy as we moved away from our source charge. Here's another way we could think of this. Okay, so what I did in white was the sort of algebraic numerical proof of losing energy. But here we could also think about it just conceptually looking at our images. So what I wrote in pink are sign conventions. This might look familiar to you from one of my slides from lesson in class. Alright, so positive work by field as well as a negative work by an external force leads to a loss of energy. Whereas a positive work by external force and a negative work by the field leads to a positive gain of energy here. So if we look at this scenario, here we have two positive charges in each other's space here. So because they're both positives, they want to repel, likes repel. So the kind of force that the field will want to exert here is towards the right. So the field will want to push on this test charge going that way. The field wants to push that way, but the external force, if an external force does exist, it always acts against the field. Because you need some external hand of God to go against the natural order of things. Okay, so the field and external force act opposite to each other. That's always a thing. Okay. So if the field wants to push to the right and our test charge is also moving to the right, that's a positive work done by the field. And on the other hand, you have an external force here that wants to push to the left, but its movement is still to the right. That's negative work. When the displacement and the force are acting in opposite directions, that's negative work. Let me do that in blue off to the side here. My little snippet about work. Oh God. Okay. So when force and distance are in the same direction, this leads into positive work. But when force and distance are in the opposite direction, that's negative work. Okay. So in our case of here of two positive charges with our test charge moving to the right away from the source charge, then here we have a loss of energy because again, field does positive work, which leads to a loss of energy, just as the external force has a negative work, negative loss of energy right there. Okay, so I'm going to show you another example of what happens when we have negative charges at play. Okay, so now we swapped out our test charge for a little negative one. So again, our initial one at original position where I drew it, still going to be K positive Q times our little negative Q over R to now lead to a negative energy. It's negative because we have to account for signs. Now when we move it to position A, it's still going to be like this. It's still going to be like a negative 1/2 of the original. Okay. And if we think about this, Is this really a gain of energy? Yes, it is. Because if we compare, -1 is still less than -0.5 if you try to put these into perspective of numbers here. So we could say, so therefore this is a gain of energy This is a positive delta U. And let's also think about it from the work perspective as well. Okay. Because these two charges are opposites, they want to attract. So the field will want to pull it or push it towards this way. Field wants to act that way. They attract, it wants to pull it in. But the external force is the one that's pushing it away. So therefore, we can see that the external force is the one that wins out. So it does positive work because it's moving the charge over to the right, whereas the field does negative work. This leads to a positive delta U. So we gained energy. The same thing with gravity. The only way we gain gravitational potential energy is by moving away from the Earth's core. We move away, and by doing so, we move away from the Earth's core, we move away from the field, the direction of the field, and we gain energy. Because remember that gravity is attractive, it pulls in, and if we elevate ourselves up, we're pulling away from that gravitational pull. So the same thing happens here for electric potential energy with electric charges. Alrighty, now if we have multiple charges in our system, more than just 2, we have 3 for example, then we could just calculate it as sort of the sum of all of the charges present. So it's a sum. Oh, forgot. New slide, gotta change to the pen. Sigma for sum. Oh boy, I keep forgetting to change pens. Alright. Sum of all the KQ1s and Q2s over R. Okay. And this could, and you don't have to take into account direction at all. You just add them up. Also take into account sign. So if there's a negative value, you just add them up, plus, minus, or etc. And I'm going to show you on the next slide of some actual example of what it would look like. We got to calculate what is the total potential energy of the system. How much energy is built up in the system to do some sort of fancy work of pushing and pulling away from each other. Okay. Alrighty, so we're just pretty much going to calculate for each of them individually. You sum up all of the individual energies between two charges. So that means we got to take into account the energy between these two charges, and these two charges. Okay, and add them all up. So we start with between Q1 and Q2, that's K Q1 Q2 over R1. So that's that taken care of. Okay, then I'm going to deal with these two charges right here in pink. That's going to be K negative Q2 times a negative Q3. Still adding them all up, but you got to take signs into account. And that's over R3. And then the one in blue will be between Q1 and Q3 right here. Okay. Still add it up. K times positive Q1 times negative Q. Ugh. Keep forgetting. Negative Q3 over R2. Alright. Now when you simplify this all up, then you gotta make sure you take into account signs. So our total potential energy is KQ1 Q2 over R1 plus KQ2 Q3 over R3 minus KQ1 Q3 over R2. Alright, so that's how it would look like. Remember that energy is the result of pairs of charges and relative to each other, so you need two charges and take into account the energy between them. Okay, so now we've arrived at electric potential, otherwise known as voltage. And disclaimer is that electric potential, bro, I hate every time I do that. Okay, electric potential is not the same as electric potential energy. Two different things. First off is that electric potential energy takes into account two charges. Electric potential is just for one charge. So if we exclude the system, it's how much energy that one particular charge has stored within itself. It's joules per coulomb, energy per unit of charge. This is also a scalar quantity. Direction doesn't matter, but signs do. So when we're adding up the total in a system, it's the same way we do with potential energy. And there's a key difference between point charges and uniform fields. That's why I have separate sections for point charges and uniform fields. Okay, and so we start with the electric potential of a point charge, and a lot of this has to do with the fact that its electric field varies with distance. So as you move further away from the point charge, then the field weakens, and this as a result also changes how we view the electric potential voltage, because voltage and electric field are definitely related to each other. And we're going to calculate this for a point charge as, keep doing this. V equals KQ over R. Simple. KQ over R, that's it. And that's for a single point charge. Another way we could actually look at it is by looking at potential energy equaling our charge times our potential difference. So the change in energy is also equal to the charge times potential difference right there. Since essentially these two equations look rather similar, you're just dividing by Q. So if we rearrange this particular equation, we get that and you could see that these two equations for comparison. Okay, and so on this slide, what we're going to look at is this specific visual example where we could calculate for the voltage at point A from this source charge, big positive Q. And this is what you get, and it's a positive value. If, let's say, we have a negative source charge, that's really ugly, I don't know how it got that shape. Okay. Also, point A a certain distance away, it's going to be a negative voltage. So that shows how signs matter here, negative voltage versus positive voltage. Okay. So in the same manner that we calculate total potential electric energy, we're going to do the same thing for total electric potential. So it's the sum of all the individual voltages. So it's Q1 over R1. So at a specific point A, it's just saying Q2 over R2 plus KQ3 over R3, etc. until you hit infinity, or however many you see there. So to find the voltage at point A, because of all these other charges, we just use the same equation from the previous slide. Or actually, in that case, for Q2, we're subtracting because it's a negative. And still adding for Q3 because it's positive. Okay, and that's what you would get to find the total voltage at point A. Now, you could also do the same thing for point B if you place a random point B here and do the same thing. And then you can even see which one comes out with a higher or lower value. So if you want to establish points of high potential versus low potential. So this is where it gets kind of tricky, but it's also fun at the same time. Again, this is a scalar, so it's easier. You just add them up, don't take into account direction. Okay, now when you have two parallel plates that are conducting with equal but opposite charges, then you have a uniform electric field being established between them. So the field doesn't diminish as you travel from one plate to the other. It's uniform. It's the same constant field. But keep in mind there's no field outside the plates. It's only between them. So the field goes from positive to negative. So electric field is uniform throughout, doesn't vary with distance, but it's definitely dependent on the separation distance between the plates. And voltage is then calculated as V equals the electric field times the distance between the two plates. V equals E times D, where D stands for the separation distance between the plates. Alright, now what we're about to see next is equipotential lines, which is how we represent electric potential, especially in relation to electric fields. Alright, so electric fields are vector arrows we draw to sort of represent direction as well as where this electrostatic force is acting, where is it strongest, where is it weakest. Equipotential, on the other hand, indicate areas of equal potential. So lines that so these lines just represent where can you move to still keep the same potential. So it doesn't take any energy or work to move these charges along the same line, but once you start jumping between lines, moving across them, then that's when you have to exert some work, whether it's by the field or by some external force. Alright. Now, the way we draw it is that they have to be perpendicular to the field lines. So on the next slide, I'm going to show you how this looks like. And it's different between single point charges, parallel plates, and even multiple charge configurations. Alright, so I'm going to draw the equipotential lines in white, whereas the electric field lines are going to be in colors. So positive source point charges typically radiate out happiness, as I usually say. Equipotential lines perpendicular to those field lines. And if you connect them, it becomes sort of like a circle right here. So anything within these circular lines are the same potential, but once you cross to a different line, then that's when it changes. You need energy. Negative charges pull in. Same spiel. Now what happens when we have multiple charges? So let's see. Okay. So the field lines are going to look like this. And equipotential lines, again, perpendicular. So it might help to just do it one field vector at a time and then connect the dots, kind of thing. Wow, this is really ugly, but you kind of get the picture. That usually you're going to see them look more like this in our typical drawings. And if, let's say, we have a positive charge and then a negative charge here, then that can tell you what kind of voltages you have. So usually on the positive end, you get positive voltages. Here it's negative. Anywhere in the middle is kind of like 0, right there. So you can tell where you have areas of high voltage, high potential, versus low potential. So positive meaning it's high, negative meaning it's low. Okay. Now if you have parallel plates, this one's easier to visualize. So field lines go down from positive to negative plate. Equipotential lines, perpendicular, they just go across. So here again you're going to have high potential at the top and low potential towards the negative side. And notice how the field vectors point in the same direction, always going from high potential to low. So it's also a natural voltage gradient, potential gradient. Kind of like other things like pressure, energy gradients, they all usually go from high to low. The natural pathway is from high to low. That's how charges flow typically, until it settles and you have no more potential difference. Okay. And that's equipotential lines. Now on our next slide, we're going to try to put it all together, put all these ideas together into a single example. Alright, so let's say we just have a random point A, which is 8 millimeters away from a positive 5 microcoulomb charge. So here what we can do, since we only have one charge with a single point there, there's no other charges present, what we can do is just immediately find the potential at point A. Okay, so potential is KQ over R. K is a constant, 9E9 times 5 microcoulombs to the negative 6. That's times 10 to the negative 6. Divided by a radius of 8 millimeters. That's 8 times 10 to the negative 3. Okay. Plug that in and you get 45 divided by 8. I wish I did easier numbers. But I always have to include the number 8 because it's my favorite. 45 divided by 8. Okay, that would get us 5.625 times 10 to the... Okay, that was positive 3. Okay, positive... Ooh, that's a lot. That's a lot of volts. A lot of joules per coulomb, man. Well, that's a really huge number of voltage. Well, we're typically not going to be working with numbers that big, but... Anyway, this is me making up numbers on the spot. So here we could see that point A has a positive voltage of over 5 million. That's a lot. Okay, now let's say we have here another point, point B. And this is definitely much further away. Let's call this 15 millimeters. Definitely not drawn to scale, just saying. Okay, so now let's calculate that one. Okay, so that's 15E negative 3. I'm giving myself easier numbers to deal with. So that's going to be 3E to the positive 6. Assuming I did this right. Yep, I did that right. Okay. Now, here we could see, based on our numbers, that A is definitely bigger than B. We can also see that this is based on distance, how voltage here is dependent on separation distance. So here we're going further away, so it's less voltage. Especially since we're moving away from a positive charge where it's usually a source of high potential. So we say that A is the higher potential and B is the lower potential. Alright, now let's say we have a negative point charge here. A negative, let's pick 7. A smaller charge of nanocoulombs. A negative 7 nanocoulomb charge that we're placing at point B. Okay, now that we got two charges here, now we're going to look at energy. How much energy is being stored up between these two? Okay. Now we're going to do this. What is their potential energy if we have our charge at point B? Okay. So it's still Q1, Q2 over R. So let's say still 9E9. I'm going to pause it here and just fast forward to the calculation. Alright, so we're going to get a negative value of negative 21 times 10 to the negative 3, assuming I did that math right in my head. Yep, that's right. And my sister just burped in the background. Don't just apologize in the background too. Okay. Oh my lord. Okay, that's negative 21 times 10 to the negative 3 joules. And that's for our potential energy at point B. Now, let's say we want to move this charge to point A. So now we're going to move this sucker up here. Okay. So that means we're going to have to calculate here what is potential energy it has at point A. Alright, and so you're going to get a number that's a bigger number but more on the negative scale. So there are a lot of things that we can draw from this. A lot of conclusions we can draw from the numbers here. And let me just move all this writing over to the side so I can have more room to write some of these conclusions down. Alright, so first of all, let's look at our energy change here. So this is considered a place of higher energy and this is considered a place of lower energy. So when we go to high to low energy, then we lost energy. Now why is this the case? So going from point B to A, that's what we're doing here. So moving our negative charge from point B to A, there are a couple of things happening here. We're moving closer to the positive charge. Okay, and so if we consider that this is a negative test charge, moving closer to something you're attracted to means field is going to push you that way. Field will push this way. External force will want to push the other way. Okay. So if we write that down there, but we're moving up, that means field did positive work, whereas the external force did negative work. Which meant this leads to a negative change in energy. So we lost energy, which we can even see with our numbers right there going from B to A. We lost energy because we're moving closer. We're letting the field do the work here. Now, isn't the natural progression, though, of charges is to move from A to B, going from high potential to low potential? That's usually the case for positive test charges, but when we're dealing with the negative test charges, the opposite rules apply to them. So it's easier, it's more natural for negative charges to go from low potential to high potential. So, oops, I gotta write that. Negative charges naturally move from low potential to high potential, whereas positive charges move from high potential to low potential. That's more natural for them. So especially when we think about whether external wins out or not, we have to also take into account the signs of these charges. So this is what it looks like putting all these things together, applying both potential energy and electric potential to these guys. Okay. Now, I hope this was helpful. It's a lot. It was rough. This is my first AP review video, so I'm making my debut into the AP world, guys. Alright, so best of luck tomorrow on the quiz. Keep in mind, quizzes allow retakes. So you got one more shot if you don't do well tomorrow. Anyway, bye-bye.